Hey everyone, welcome back to Code in Motion. Today we're looking at one of my favorite LeetCode problems, number 104, maximum depth of a binary tree. So given the root of a binary tree, return its maximum depth. This is easier seen with an example, so let's take a look at the diagram. We have the root 3, and the maximum depth in this case is 3. The reason being one node over here, 2 nodes, and 3 nodes. You can either take 327 and call that 3 as the maximum depth, or you can take 32015. But the reason why we ignore 9 is because that's a depth of 2, but in this case on the right side we have a depth of 3. So we want to know the maximum depth of a binary tree. So remember, there are 3 ways to traverse a binary tree. You can use the pre-order, the in-order, or post-order traversals. In this case, we're going to use a post-order traversal because we need to know the left max depth and the right max depth before we return back the current max depth, okay? And so with the post order, we're gonna explore nodes 9 and 20 before we return back the result for node 3. So let's see how this looks. We start out by scanning 3, and then we need to know the left depth. So we go to node 9. We scan node 9, we need to know the left depth. So we go to the left child of node 9, which is null. In this case, this is our base case, right? So null has a depth of 0, so we update the left depth to 0 for node 9. So let's update that. And now we find the right depth for node 9. Once again, this is a null value, and this is the base case of 0. So the right depth is 0 for node 9. And now, what does that mean? What is the max depth at node 9? The left and right depth is 0. Well, this is the formula. You always take the maximum between the left depth and the right depth, and you simply add 1 to it, because node 9 counts as a node, right? It counts to the overall depth. So whatever your previous results were, you simply add 1 to that. And so for node 9, the depth is 1. And that's what gets returned back to node 3 as the left depth. So let's update that at 3 to 1. This is what the result we got back from 9. Now we still need to find the right depth, right? This is why this is a post-order traversal. Even though we're scanning node 3, we really scan the left and right subchildren first. So now let's go to node 20 to find the right depth. And now at node 20, we need to find the left depth. So we go to node 15. At node 15, we need to find the left depth. And this is the base case of null. So we get back 0 for the left depth. So let's update that in the diagram. And let's get the right depth at node 15, which is 0 as well. So we're going to put that in the diagram. And then we're going to ask ourselves, what is the depth at 15? Well, it's 1 plus the max left and right depth. In this case, they're both 0, so it's just 1. Now, this depth is the left depth for node 20, right? So let's put that in. And at node 20, we now need to know the right depth. So let's go to node 7. We're going to do the same exact thing that we did for 9 and 15. So find the left depth, which is 0. And we're going to put that in the graph. And then let's go to the right node, or the right depth. And that's also 0. So let's add it into our diagram. And the depth at node 7 is 1. So let's put that in there as well. And then let's return that value as node 20's right depth. So we have 1. Now this is where things get interesting. For node 20, this is going to be 2. It has a depth of 2. 1 plus the maximum between the left and right depth, which are both 1. So the depth at 20 is 2, and we return that back as the right depth to node 3. Right? So now the right depth is 2 for node 3. And what do we return back for node 3? This is 1 plus the maximum between the left and right depth. In this case, the right depth is greater than the left depth. So we use 2. 2 plus 1 is 3. So the current depth at node 3 is 3. And now we want to look at the space and time complexity. This runs in O of n time and O of n space. The reason this is O of n is because we scanned the entire tree. And you might think, why is the space O of n? Well, it's actually the recursive stack. We're going to make recursive calls. And in the worst case, if this was a skewed tree, as if it were a linked list, for example. If you only had left and right subchildren, the recursive stack would be length n. So the reason I love this problem is because it's actually so easy to code out once you get used to the recursive calls. So the base case is if your root is null or your node is null. So if not root, this is the base case. We return back 0, right? But if you do actually have a node that's not null, you first need to find the left depth. So the left depth is equal to self.maxDepth. I'm going to recall this function on root.left, which is just node.left. And over here, I'm going to say the right depth is equal to self.maxDepth of root.right. Right? This is the post-order traversal. First, I explore left, then I explore right, and I'm only going to start doing my business logic after I went through both right and left. And in this case, what was the formula we used? It's 1 plus the maximum between my left depth and my right depth. And that's it. It's basically 3 lines of code, is almost the entire algorithm. And if we run this just to verify it succeeds, we get confirmation. Thank you so much. If you guys are interested in more LeetCode style animations for the blind 75 list, be sure to subscribe and like below. It means a lot to me. Thank you so much.